Alright everyone, so today we're going to be going over how to use the inputs and outputs of the board, more specifically PWM. So on our board, we've got switches, we've got buttons, so yeah, on our board we have switches, we have buttons, and we've learned how to use those. But one thing that when I took DSD was never taught was how to use the inputs and outputs. So that's what this video is going to be about. So okay, so this here is a program that's going to use pulse width modulation to get an output. So it's here on the notepad and it's also in the background. But let's go over some theory and to review how this all works. So there's two kinds of signals. There's digital and there's analog. Let's say we have a plot. So the x-axis is going to be time. Y-axis is going to be voltage. So you might ask yourself, well, what's a digital waveform? Digital waveform is going to be something like this, where it's just ones and zeros. It's either high or it's low. No other value in between that. Analog, it's going to be something like this. It could be anything. So our board here, this board can only do digital. If you want to do an output, it can only output a 0 or 1. So you might be asking yourself, well, what if you don't want 1 volt there? What if you want 5.7, or what if you want 2.8 volts there? Actually, for this board, it's more like this. You can either output 3.3 volts or 0 volts. So usually it's 1 or 0, but for this board, it can do only 3.3 or 0 and nothing in between. It's still digital because it's either it's like this. It's either 3.3 or 0. You might be asking yourself, well, how do you input something that's in between that value? Like, how would you do just a constant 1.6 volts? Well, the way you do that is with pulse width modulation. And essentially what that is you only have it on for some time and then turn it off for the rest of the time. So So for this waveform here, we can do this, right? With our board, since it's digital, for some time we turn it on, other time we turn it off. If we turn it on for half the time, we're going to get half of 3.3. So if we were to physically put our multimeter here, it would read around 1.65 or something like that, which is half of this. We want to do less, we want to do 0.8 volts, or around that much. Then what you would do is you would only turn it on for 1/4 of the time. Okay, we're making good time. So if you turn it on for only 1/4 of the time, then you get 1/4 of the maximum. So yeah, you get the point now. So that what this program does is there's two main inputs, the switch and the output of the board, JA1, which is right here. And you map that in the constraint file by doing this. So first, you should declare it as an output. Then you tell it where on the board you want it to be an output. In this case, it's going to be right here. So we want in the PMOD header JA. If you zoom in, you see right there that it says JA, and JA1 is this first one. So by doing that, it assigns it as an output. Okay, so let's get on to the rest of the code now. So we're going to be using register X to be the value that determines whether or not this output here is going to be high or low. Oh yeah, so that's this, JA1. If we want JA to be equal to 1 or 3.3, X has to be equal to 1. So what I have here is a counter where Q is a register that is going to be incremented up. And whenever Q is less than or equal to the value of the switch, so whenever Q is less than or equal to the value that the binary value we put on the switch, X is going to be equal to 1. Whenever Q is greater, it's going to be 0, which will meaning this is always 0, meaning the voltage across this is 0. Go through what's actually happening. Megahertz clock, just ticking like this. So Q might be equal to 0 there, Q might be equal to 1 here. And the reason why it increments is because every positive edge of the clock. So this right here, this is a positive edge, this is a positive edge, this is a positive edge, and this and this and this and so forth. So at every positive edge, Q is going to be incremented. So Q is equal to 2 there, Q is equal to 3 there, 4 there, right there. It's going to go on and on. So Q is equal to whatever the maximum of 11 bits is. So since there's 11 bits, 2 to the 11 equals, we'll just write as 2 to the 11. Because like if we have 3 bits, 1, 2, 3, that number is 7. So let's see if that formula works. So 2 times 2 is 4 times 2. 8 is minus 1. So this is the formula. So 2 to the 11 minus 1. Let's just verify that real quick. All right, here, yes. So it's 2 to the n minus 1. So since we declared Q to have 11 bits at the top, it's going to count all the way up to 2 to the 11 minus 1, whatever that value is. And then it's just going to restart. And then do the whole thing again and again. So once we get here, once we get right here, it's going to reset and count all the way up again and then reset and just keep doing that. So then we have our 10-bit binary switch value, which I'll represent right here. So whenever Q is less than the switch, X is going to be equal to 1. So let's say we want to do this up here, where it's on only half the time. Then what we're gonna need to do is make it be such that the value on this switch is greater than the value of Q for half the time. And we know that Q is equal to 0 at the start. Q is equal to 2 to the 11 minus 1 at the end, which is equal to, in binary, so at the start it's equal to 11 tick B 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then here it's 1 tick B 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we know at the start Q is equal to 0 there, and at the very end it's equal to it there. And we know it's incrementing by 1 evenly. So what about in the middle? What about in the middle? In the middle center, Q is equal to 2 to the 11 minus 1 over 2. And in binary, that's equal to this. So if we set our switch to be equal to, so this is SW, if we set to be equal, then what that's going to do is then that means this if statement is going to be always true, since Q will always be less than or equal to the value switched, so X will always be equal to 1, meaning this here is always going to be outputting the highest possible value. It's always going to be 3.3. So we're going to see a 3.3 volt output if we do that. But let's say we change switch to be equal to 0, and then the rest ones. Well, then what that means is, that for this half of the time, switch is going to be smaller than Q. Let's do a timing diagram. Move all this down. Let's switch to this here. It means that for the entirety of the time, switch is going to be equal to that value. It's T. And for half the time, value that's less than that number. going to be greater than that number. This is going to happen. Say we set switch to be equal to this. Well then, so we have Q is equal to 0 at the start, 2 to the minus 1 at the end. So this is like our our timeline of the entire thing, where the value we set switch equal to gonna be what cuts it off. So if we set switch equal to this right here, where do you think on the number line it's going to cut it off? It's going to cut it off here. And if it cuts it off there, then that means this statement will be true for only 1/4 of the time, meaning only 1/4 of the maximum output of 3.3 volts is going to be shown. So yeah, that's how that works. So let's do a demonstration real quick. You got a multimeter. Was if we put this switch input combination, we're going to get 0.8 volts. So let's do that. 2, starting 2 are 0, the rest 1. So when we put our multimeter to measure the voltage from here to here, we should get around 0.8. Let me just use my hands, both hands, to measure it. So yeah, it's about 0.8. And let's turn the other switch on. So now it should go up to be around 1.6. And let's turn all the switches on. So it should be 3.3 now. Let me just measure it again. Yeah, around 3.3. So I hope that explains how to do pulse width modulation using the outputs.